Hey everyone, and welcome back to the TDS Data Science Podcast. Now, it's no secret that AI systems are being used in more and more high-stakes applications these days. And as AI eats the world, it's becoming critical to ensure that those systems behave robustly, that they don't get thrown off by unusual inputs and start spitting out harmful predictions or recommending dangerous courses of action. If we're going to have AI drive us to work, for example, or decide who gets bank loans and who doesn't, then we better be confident that our AI systems aren't going to fail because of some freak blizzard or because some intern missed a minus sign. So we're really past the point where companies can afford to treat AI development like a glorified Kaggle competition where the only thing that matters is how well models perform on a testing set. Now, fortunately, AI risk is starting to get more attention these days. New companies like Robust Intelligence are stepping up to develop strategies that anticipate AI failures and mitigate their effects. Now, joining me today is Yaron Singer, a former Googler and professor of computer science and applied math at Harvard, and now the CEO and co-founder of Robust Intelligence. Now, Yaron has the rare combination of theoretical and engineering expertise that you really need to understand what AI risk is, and the product intuition to know how to integrate that understanding into solutions that can help developers and companies deal with AI risk. And he joins me to talk about what AI risk is, the cost of AI failure, and how to avoid it on this episode of the TDS Data Science Podcast. We talk to a lot of people on the podcast who are focused on AI robustness, AI safety, AI alignment, that sort of thing, but rarely people who are actually trying to implement these things in real systems for commercial purposes. And I think there's a lot to be gleaned from that experience that you have. I think it's anyway, a very rich area for conversation. So I'm looking forward to it.
No, awesome. Same here. And I'm a huge fan of this podcast. I follow it. I drive like 40 minutes every day to our office. So I get my kind of my dose of podcasts. So I'm a big fan.
I appreciate it. So one I think recurring theme in your work is this idea of AI risk, defining AI risk, and we will get to all that. I think, again, rich conversation there, but I do want to get a sense first for what brought you to this space. Like, you have a long history in research, and the idea of AI risk becoming a focal point is always interesting to me because there are interesting thought lines that people tend to have that get them there. What was yours? Like, what was your journey into AI risk as a field?
I've been looking at this area of AI risk, which at the time I didn't realize it was called AI risk. It was about the potential failure modes of machine learning. So I think it's been like, now when I look back on it, it's been like 9 years almost. So right now I'm CEO and co-founder here at Robust Intelligence. But before doing that, I was a tenured professor of computer science and applied math at Harvard, and I still am. And before that, I was, I spent some time at Google, and that's kind of when I really saw just how like bad this problem can be. So I've been working on designing algorithms, right, that are making decisions on top of input that's coming from machine learning models. And when you do that, you start asking yourself, well, like always, you want to have formal guarantees about your algorithms, and you start asking yourself, well, what happens if the machine learning model gets something wrong, right? And then you start asking yourself, well, what happens if there's some sort of little bit of erroneous input into this machine learning model? Like, how is my algorithmic decision going to be dependent on that? And then when you start looking at that, then you realize that we have no formal guarantees, and it's the problem is actually kind of quite severe. I really dived into this problem and have been working on it ever since. And I've been really looking at what is it that we can guarantee from whenever we're making algorithmic decisions that are coming from machine learning input, and what happens if that input is a little bit distorted or erroneous, or for kind of all its forms. And then initially it was it was an academic endeavor. Right. But then as AI has gotten, much more, traction and adoption, it has become kind of like a bigger issue. So I think that's kind of, at first I was intrigued by this, as from a purely academic perspective. But, over the years, it sort of morphed from this like academic question and sort of, and instead of like algorithmic challenges, into a real kind of, I think, societal problem. Right. Which we now sort of call AI risk.
Well, and even defining this area of AI risk is its own rabbit hole, and that's something we're going to get to. One thing I would love to get from you then, for listeners who might have a broad sense of what AI failures mean and what that might look like, but not a specific sense. I'm curious if you have examples of like what is a classic AI failure, and then what are some of the sorts of things that you might want to be able to guarantee about the behavior of AI systems to avoid those sorts of failures?
Generally speaking, what does it mean that like AI failure, right? I'm going to use the terms like AI and machine learning interchangeably. So, let's say that we have some sort of machine learning model, not necessarily a deep learning model. It can be regression. It can be a simple classification model. Basically, AI failure means that the model is making is spitting out a prediction, right? But that prediction is wrong. Well, how do we know that it's wrong? How do we define that's wrong? Well, for that input, we're not expecting to get that output. So that's kind of like how we define AI failures, right? Like you have an AI model or machine learning model making a prediction, but that prediction is wrong, right? And it's not because the model hasn't been trained properly or we haven't used like a deep enough neural network. It's about the fact that there's something unexpected that happened between the input and the actual model that causes this this model to spit out an erroneous prediction. When you're talking about guarantees, there's an entire set of like formal guarantees that you can talk about, and you can have like a lot of definitions and do a lot of proofs. But really what we want is to be able to live in a world where our existing AI models are somewhat protected, right? So that even when there's some sort of some mismatch happening between input of the model to the actual model, the prediction is not that far off from where we would expect it to be.
One of the through lines that I'm hearing here too is you alluded to this idea that it's not because the neural network isn't deep enough. It's not just because there isn't enough data or something sloppy was done. It's that there's some sort of like out of distribution issue where the inputs that the system was trained on are subtly different, but importantly different from those that it encounters in production. And then you end up with an error that doesn't reflect human error, I guess, in a way, but there's a more fundamental source to it. Is that fair?
Sure, but it can also be human error, right? So some errors can just be like, exactly like you're saying, there's distributional drift, right? Maybe, we made predictions on the number of customers that, they're going to walk through the door, and we're using that model. But then, COVID hits and now our models don't work anymore. It's a serious distributional drift we haven't accounted for. The models are producing erroneous decisions. That's one kind. But then there are other kinds of like distributional drifts that sometimes you can attribute them to like human error, but those things happen all the time. Missing feature, somebody puts in the wrong currency, the formatting of the data changes in some sort of way that you can't expect, right? And it kind of goes through the entire system, and then it meets the model, and the model is doesn't know that now the currency is in yens versus US dollars, and it makes a prediction. That's a distributional drift. You can attribute it to like human error, but it doesn't really matter, right?
And I guess one of the defining characteristics of these sorts of errors is the fact that they're typically silent, right? Like we're used to in software engineering. Many errors, not all, but many are much louder. So you'll get an error message or a warning or something like that. So how does the fact that you have this feature of silence in machine learning, how does that affect the impact that these bad predictions or failures can have on live systems?
Yeah, that's a great question, right? The way that we define silent errors is basically by saying that input is coming into the model, and then there's output coming out from the model. A set of features coming in, or you have an image or a sentence or whatever, and then the model spits out a prediction. There's a number, right? So from a software engineering perspective, everything is okay. Input in, right? Output out. It's all good, right? The only problem is that the output could be garbage, right? Or the output could just be it's just wrong, right? That number is wrong. So we call that a silent failure because there are no bells and whistles that go off when this happens, because the model is spitting out a prediction. In some cases, it's easier to detect because all of a sudden all your inputs are producing erroneous outputs, right? But in some cases it's harder to predict. It's harder to see because 1 out of 10 inputs, 1 out of 100 inputs, 1 out of 1,000 inputs are doing this or causing these sort of these errors. And all of a sudden, the model, the prediction drops, right? And decisions we're making kind of like wrong decisions down the line. And it's much harder to go back and identify, well, what happened 3 months ago, 6 months ago, 7 months ago, who knows when, right? To sort of start looking at, and debugging, like what happened, that the model changes its output on some of the inputs, right? And you see that all the time, right? And if you think about the number of engineering hours that go into like debugging these models, it's huge, and it's a real problem.
The sort of number of engineering hours, that does make me think of how my own software engineering skills reluctantly improved when I was forced to embrace test-driven development. Like this idea that you write your unit tests before you write your software, and then this makes it so that you're doing a lot less debugging after the fact. Do you see testing as a big part of the solution on the machine learning side? Like, are we missing test-driven development for machine learning, and is that part of the solution here?
Yes, absolutely, we are. Test-driven development is something that is it's a practice that is very very pervasive in software engineering, as you said. But machine learning is as an engineering discipline, right? It's a much younger discipline, right? If you think about if we think about software engineering, it's it's something that we've been doing for like 50 years. We've developing kind of practices, and we created a kind of like set of norms that lead to kind of like strong software systems and strong software development. Machine learning is a much younger discipline, and it's also kind of like this big melting pot. As you may well know, not everybody comes from software engineering background. Actually, most people most people don't, right? Like there are people that come from like diverse backgrounds, like some like can come from physics, right, or or data science, right, and statistics, like all these different disciplines, right? And we all meet together and and develop these models. And test-driven approaches are things that we don't have that right now in machine learning, and it's much harder to do. We know how to write unit tests for software. It's much easier to rationalize about the space of inputs that can fool your function. But when we're talking about statistical models, it's much harder to imagine the sort of the set of things that that could cause a model to break.
And does that force you to triage a little bit, I guess? Because somehow you have to decide which tests to run, which errors like are going to be really high impact and probable enough that they're worth targeting. And then like, what is that long tail where it's like, yeah, things might go wrong in this direction, but we've got a team of a certain size. We can't worry about those sorts of things. Like, how do you think through those trade-offs? And I mean, if you have examples of the sorts of errors maybe that you think of as high priority, that might be really interesting.
I think that it really depends on the application, right? And specifically, you sort of have to ask yourself, like, what is your threat vector in some sense, right? And how do you weigh about outcome? And you can think about like kind of different scenarios. So one scenario is like, you can say, let's say you're using predictions for doing online marketing and targeting of certain profiles or whatnot. In that world, you can argue that it's not the end of the world if if you make a mistake. Even though I would argue that that's not necessarily the case. I can argue and give you examples of cases where you're making a wrong prediction, and it's something that like hurts users like very much, but you can just sort of think about this in terms of like dollars and cents. You can say, well, I have like a lot of users, and I'm making a lot of predictions, and making a mistake is not that big of a deal, right? On the other hand, you can think about like if you're an insurance company and now you're using statistical models to make predictions about who you're going to insure, who you're going to give life insurance to, or things like that. And if now you're making a wrong prediction, whether it's because of the distributional drift, or because your model is biased, or because you switched between age and year of birth, then those things can have like dramatic implications on people's lives. The threat vector is different, right? So I think like ultimately you want to think about like what are the threat vectors, or kind of like what are the potential bad inputs that we imagine that we can see, right? And weigh that against like what is the potential harm that we get from a bad prediction.
This is where I get really interested in robust intelligence as a company, because one of the challenges that I remember from like my days of like startupping work is you're always weighing like how much bespoke work are we going to do to tailor a solution to a particular company versus how much of this can actually be turned into software that generalizes. And so because we have, as you said, all these fairly bespoke problems or specific problems that are domain specific, there are solutions that are domain specific too. So how do you reason through like that trade-off of generality in software versus sort of consulting and more tailored, customized stuff?
Yeah, that's a great question. I think that, in general, like developing machine learning models, right, is something that a lot of times is unique to like a specific application or use case, right? Certain data set. And a lot of times, like, when we're talking about developing models for the sake of predictive performance, right? That's something that's hard to productize. What we're saying is that like when it comes to protecting models and testing models, it lends itself like very naturally to automation and productization, right? Because at the end of the day, input to tabular models pretty much looks the same, right?
Yeah.
And there's a finite set of tasks, that people do with, tabular models, right? And from our perspective, we're completely agnostic to what these models do and how they're used. What we do is we build models that protect these models from making mistakes. We build a set of like tests that test these models like in an automated way, in a way that doesn't even require us to look at the data or look at the models. So what we're seeing that like this part of like protecting models, testing models, lends itself very naturally to automation and just like a generic product.
What are some examples of those tests that seem to generalize really well? Like, are there patterns that you found, like a certain type of error class comes up a lot, and so you can pretty universally apply those tests?
I think it's kind of like what you expect. There's sort of like, it's like a power law distribution in that, like, we have, so basically, so what do we do in the company? What we do in the company is we build an AI firewall, right? And that AI firewall is a piece of software that wraps around a model to protect the model from making mistakes, right? How do we create this magical box that can protect your model like from making mistakes? Well, we train that AI firewall, and the way that we train that AI firewall is by running tests, by running stress testing on your models, on your AI models. We basically run a series of tests and we quantify like how the model behaves to different changes in input, whether these changes are changes that already occur in your own data or changes that that we initiate through our algorithms. Basically, what we do is we write a lot of tests. We test for distributional drift. We test for missing features. We test for capitalization errors. But then there's like when you're looking at what are the tests that identify the most issues? There's a recurring pattern. There's like kind of like this power law distribution where you sort of see the same tests finding errors like over and over again. Most models are sensitive to the same kinds of things.
It's interesting that is a pattern and sort of reassuring to some degree, at least that there's a lot of low-hanging fruit.
Yes. But by the way, like when you think about it, we know why, right? We use scikit-learn, right? And there's a certain implementation of XGBoost. It's a great implementation, but that implementation is sensitive. And wherever you're using it, whatever variant you're using of this XGBoost, right? Or whatever, right? It's going to be like sensitive and vulnerable to the same kinds of things, right? So at the end of the day, right, like we're relying on a finite number of model types, and every model type like kind of fails in kind of like in its own way.
That also makes me wonder, like, is there a consistency across model types? Like, does a deep neural network tend to fail in the same way as a support vector machine, let's say, or are they very different?
That's a good question. We've done a lot of like analysis on it, and we have some blog posts on it. But like, there are some failures that like all models, that basically they happen. Irrespective of the architecture of the model, and some that are very specific to the model type, right? So like there'll be like some failure modes that only exist in SVMs, and some failure modes that only exist in for deep neural networks, right? We can talk about the common patterns of ways in which models fail. What we currently know as machine learning community, when we're building models, we have pre-processing when we're putting in front of models. And there is some power that we can give pre-processing, right? So with pre-processing, we can check for certain things. We can check whether, there's like integer overflow or, like certain basic things like that. So these are the things we can kind of protect our models from. We can protect our models from like, very large integers. We can protect our models from, things like maybe like a missing feature. We can turn that into like a null, right? Those are things that we can, the pre-processing does. And then, whether we're using an SVM or deep neural network, like those things are going to work. Places where models fail are places where basically this pre-processing needs to have some sort of context about the data and context about the model, right? And what I mean about context is like, we're talking about distributional drift. So now as input, there's like a very large number or there's like a negative number. Pre-processing alone, without seeing the data, right, that the model works on, pre-processing doesn't know whether a negative number is valid input. So it passes it through, right? And that can be like, popular failure mode for models, right? And same with like a very large, number, right? Again, it doesn't know whether like a very large number, as long as it's not integer overflow, right? It doesn't know if it's like legal input, right? So let's say that one of your features is age, right? And now instead of like age, it sees like year of birth, right? This is an example that actually happens. Instead of like, age 36, you now see the year of birth like 1985 or 1986. Pre-processing doesn't know whether 1985 is like its legal input, right? It's a number. Yeah. It's in order to have like so basically like pre-processing needs context, right? And the context that pre-processing needs basically comes from the data and the model. And that's exactly how we build the AI firewall, right? The way that we build the AI firewall is we feed it with the data, and that's how we train, right, this AI firewall on what is like legal input versus what is out of distribution, what is wildly out of distribution, and we measure its effects on the model to sort of see, if I have something that's out of distribution on this feature, is it going to affect the model performance? That's a very popular way of models failing. They have pre-processing, but that pre-processing lives without context, right? And that's how you can fool them, regardless of what the model architecture is.
Yeah, it seems really helpful to, separate out the pre-processing from the actual model kind of number crunching itself. It also seems to suggest, based on your answer, that's really interesting. So correct me if I'm wrong, but I sort of see three different parallel lines of effort here. So first, we've talked about the testing. So writing literal tests that check, as you said, for like nans and infinities and so on. The second is a sort of like anomaly detection piece where you're describing, okay, how do we, given a sample, we know what the training set looks like. Maybe we train an anomaly detection algorithm, and now we know, okay, we've got a new sample, and it's like, it's being flagged as an anomaly. This is probably going to be out of distribution. Let's be careful with this. But then as a third line of effort, it sort of seems like a lot of this overlaps with the idea of fuzzers. So like I've been spending my time reading, for various reasons, cybersecurity stuff. And if people don't know what a fuzzer is, like it's basically a system that usually historically spits out randomly generated inputs in the hopes of trying to break another system. So throw all these random inputs.
Very much so. Yeah.
Okay. So
it's a great idea. Yeah. And then this is, by the way, like, I think we don't talk about it a lot, but like there's a lot of effort going into this exactly this fuzzing. Basically what we do is we design algorithms to identify, part of the tests are just like, perturbations, like random perturbations, to see like the effect of random perturbations on, with like different distributions, to see like these effects on the model. Some of the tests that we run are basically, what we're doing is we're designing algorithms. And the whole purpose of these algorithms is to like identify feasible input that like you would actually see, manipulating that input in a way that remains, quote unquote feasible, but succeeds in fooling the model like dramatically. And doing that efficiently, it's a very large search space, and doing that efficiently is a challenging algorithm problem. So that's something that we spend a lot of effort on. And for companies that are, worried about adversarial actors, right? So if you're doing payment processing, if you're a large internet company and you're worried about bots and then things like that, right? So you're experiencing input that a small fraction of it comes from actors that are actually trying to manipulate their input in ways that will fool your models that are trying to detect this bad behavior. And these are companies that like very much care about not only fuzzing, but these algorithms and these tests, right, that actually identify the vulnerabilities of models.
The adversarial AI piece is really interesting. I'm curious about your thoughts about how that fits in with, I don't know how to call it, like innocent model failures, where some user, like you said, enters 1985 and like their birth year instead of their birth date, and that causes obviously a catastrophic failure. How do you distinguish between that and something that's maliciously intended? Do you use the same mechanisms to defend against it, or is it one size fits all?
Yeah, that's a great question. So initially, we were more focused on the adversarial case because that's where we said, okay, let's go to the worst case here, and we work with companies that that worry about the adversarial input part. But then what we saw is we talked to like a lot of companies, and they're like, well, yes, I understand that my model can fail in this way, but I don't have like any bad actors like internally that are fooling my models. But what I do have is I have like wrong currency being fed in, or I have like or people are training models, using one type of data that they're finding online, but then there's a mismatch between that data and the data that we're actually seeing coming from customers, and that creates problems. So, and what we realize that the infrastructure is identical, right? And also, in some sense, like the problem is the same as well, because these organizations, what's happening to all these organizations is that once they're implementing AI, they're inheriting AI risk. Where that risk is coming from doesn't really matter. It doesn't really matter whether now somebody's like, it's somebody who's like intentionally manipulating the input, right? Or the input has been, changed or manipulated because of, it's been fed wrong, or there's some sort of like change in the data collection method, or, what have you, right? What's common is like, irrespective of why these mistakes are happening, these mistakes are happening. These organizations are, experiencing risk, and basically every one of these, these set of risks can be mitigated through like a properly designed test. So as long as you can kind of like create properly designed tests for, detecting, various kinds of anomalies that are coming from, adversarial input, or anomalies that are coming from like distributional drift, or, missing features and whatnot, then you're able to protect an organization from AI risk.
Actually, that organizational perspective is also a really interesting aspect of this whole discussion, because I imagine as the impact of AI failures gets larger and larger, as it is, we're relying on AI systems for more and more mission critical stuff, in some cases safety critical stuff. The risk that's faced by companies that are implementing these algorithms starts to grow. And I imagine eventually it grows to the point where you need like executive level awareness of this risk. Like it's no longer enough to just have a technical team that's like, oh yeah, we've got our 3 people in the ML team and we can trust them to look after the obvious failure modes. Like at some point there's reputational risk, brand risk, like all kinds of things, even criminal risk in the limit. Is that kind of increasing risk profile something that you've seen? And do you have a view on like organizationally, like should there be, I don't know, a chief like AI risk officer? Should there be people whose like executive and full-time function is to focus on this sort of thing?
Absolutely. So that's a great question. So I can tell you that like, as a company that sells a product that, solves, AI risk for companies, we end up interacting with executives from, all the way from C-level to, the VPs to the directors, managers of data science, and the data scientists who are actually, using and running the product. For us, for data scientists, for machine learning engineers, and I count myself as one of them, right? It's a technical problem, right? We're building models. These models are failing, right? How can we stop them, from failing? It's a technical challenge. And basically, in our product, comes to solve, that technical challenge, that these organizations have, that the data scientists have, in a way that basically saves them 25 to 40% of their time, so that they don't have to deal with that, right? So they can go back to like, focusing on building models, right? But I think kind of what's more interesting is what's happening at the VP level and the C level, right? Mm-hmm. And at the VP level, at the C level in these organizations, yes, they're aware of the technical problem and the technical challenge, but for them, the impact that it has on the business, the reputational impact, the monetary impact is a much bigger factor. So we're seeing like our buyers are it's the C levels and the VPs, because they're really worried about AI risk, right? And we're already seeing, not only are we seeing kind of involvement, the chief data officer at this company, or the head of AI at this company, like who's sort of like whose mission is to like de-risk the organization, from AI risk. But we're also starting to see companies specifically hiring people for these roles. I don't like to make the predictions, but I think that a few years from now, in the same way that we have CISOs in organizations, I think that we're going to have some type of like, chief of AI risk, chief of AI compliance. We're going to have these roles, right? Because also regulation is pretty much forcing us to as well.
I definitely agree with that prediction. It's consistent with a lot of the stuff that we've been seeing as well. It's really fascinating to see that kind of early adoption ahead of regulation, people starting to realize that this might just be a thing. I also kind of feel like it's in a way related to general concerns about what the level of responsibility and capability that AI teams might have. Like if C-level people could look at their AI teams in some cases, not in all, but in some cases, they might be shocked at like how impactful a lot of their choices day to day are, and just the level of essentially executive function that they're implicitly taking on, and sort of enshrining that anyway and recognizing it in the organizational structure seems to make a lot of sense.
Yeah, I totally agree. And that's kind of like really something that we've, that we realized as we were doing this. Like, again, when I started looking at this, it was like a really interesting, in the beginning, it was just like a really interesting theoretical problem. It's a super interesting theoretical problem, like different ways that you can, the sensitivity of machine learning models, and, and what you can and cannot do, to kind of like protect it. But as we're doing this as a company, I think that's really something that we're realizing. And I think it's exactly what you're saying, is that like, just how much risk organizations are adopting, right? Or kind of like taking upon themselves when they're putting these sort of statistical functions, right? Inside the organizations that are, making, like very important decisions. And when we're looking kind of from a societal level, when we're thinking kind of a few years ahead, right? The way that the world, is going, and, whether we like it or not, it's just, we're going in a direction that's like very dependent on, algorithmic decision making, right? That relies on, on statistical machine learning models. So I think there's already a lot of risk, that we're taking upon ourselves, and that risk isn't going away. I think it's just, I think we're just taking on more and more risk.
On the practical side too, so the firewall that you've described, essentially you have data that comes in, and the firewall's job is to flag that data as, let's say, being highly likely to mess with the model and result in a garbage output. The user inputs some data, and I guess in some cases, they'll have to get some signal back that, hey, we haven't generated a prediction for you because of some failure that we caught. I imagine that's its own challenge, right? Communicating this to the end user, and maybe that's a challenge for the company, that your customers. But do you have any thoughts on how that's best done, or in what context it can be important to think about?
Yeah, so that's a good question. So I think, right, the question is like, okay, so we put an AI firewall in front of a model. There's some kind of like, the AI firewall identifies some sort of error. What do you do then? Basically, there are various options that the AI firewall gives, right? One option is, just flag it, right? And, you flag it, it comes, and then, it comes up in the, in the UI, you can see it, and then you can see what happens like over time. The other aspect is like, you can block it, right? And the user can decide like, how they want to deal with it, but you can block like bad input. And sometimes it makes sense, right? And again, you sort of see in the UI that it was blocked. Another aspect, what we also do is, we basically give a score, right? And that score is like, we don't only, block or flag. Basically what we do is like, the goal like of the AI firewall is to produce a score in every data point. And that score is like, what's the probability that this data point is gonna lead to a, substantially like erroneous prediction, right? Mm-hmm. And then basically with that score, the user can basically ensemble that with a model, right? To basically reassess the prediction, right?
Okay.
So that's another option of like the ensembling. And the final like option that we give is, we also give an imputation option, right? Where if there's something like let's go back to our kind of like replacing age with year of birth, right? then now you sort of see something that doesn't make sense, like your birth. Then what we do is we impute it with a value that does make sense, conditioned on that data point, right? So the AI file is pretty rich in kind of like what it offers, right? Because we know that like different applications like have different constraints, right? So that's kind of like how we deal with that question.
Yeah, I really like that. It sort of brings everything full circle from this like highly theoretical question to how the decisions are made internally and then how that's even fed to the end user, and it becomes this product question, which again I find really exciting. I mean, I feel like this space in industry is one that's going to grow very, very quickly and very significantly, and I think it really is an ethical imperative too. I mean, we need to have more focus on this kind of stuff. We can't have a future where AI systems are being depended on for, in some cases, life or death decisions or just finance or no finance decisions when we don't have a way to verify the robustness of these systems. So exciting that you're working on this, and thanks so much for sharing your thoughts here on the podcast.
No, absolutely. Thanks for having me here. It's been again, I'm a fan of the podcast. So I'm really happy to be here.